All right. Thanks everyone for coming. My name is Charlie Shobe. I will be chairing today with Michal Ben Israel and Rebecca Harries. And we are very excited today to welcome Abby Langston from Kansas State University. Abby did her undergraduate work at the University of Maryland, followed by a master's at the University of Florida. Abby then did her PhD at the University of Colorado before moving on to become a visiting scientist at Wageningen University, in the Netherlands, before then moving back across the pond to Kansas State University, where she is now an assistant professor. So we're very excited to have Abby here to tell us about beyond lithologic control of bedrock valley width. So just a couple of notes before we dive in. We are going to have the chat turned off for sort of the majority of the talk here. We will then turn the chat on a few minutes before Abby wraps up, so you can start kind of cogitating on your questions. If you want to raise your hand to ask a question after the talk is over, we'd be happy to have you do that, or we can read out questions that you put in the chat. All right, so I will turn it over to Abby. Thank you so much for joining us. We're really excited to have you, Abby.
Thanks, Charlie. Can you hear me okay? Yeah, okay, I'm gonna share my screen. There we go, is that looking good?
Yes, that looks great, thanks.
Okay. Okay, get my kind of Skype window arranged. Okay, thanks, Charlie. Thanks, Charlie, for that introduction, and thanks to everyone who has joined us here today. So I have a long sort of scientific title of my talk, but I'd like to subtitle my talk just with these simple questions. How are wide bedrock valleys formed, and what factors influence wide bedrock valley development? So I like to start by thanking my collaborators. Nobody can do it alone. I certainly didn't do this research alone. So I'd like to thank Untitled Chapter from my department here at Kansas State, Jill Marshall from the University of Arkansas, Christina Newdorf and Amanda Kuhn-Siebert from DRI, and my three awesome former and current grad students who have helped me on these projects. Okay, so for a quick outline of what I'll be talking about today, first, I'm going to do just a little bit of background on bedrock incision and what we currently know about the development of wide bedrock valleys. Then I will do a quick introduction to these end member mechanisms of bedrock valley formation. Then I'll talk about two studies that further develop these ideas of the end members of valley widening. And then I will wrap up by talking about some preliminary data from a brand new research project on the Buffalo River in Arkansas with Jill that I'm really excited to talk about. So first of all, just bedrock rivers. Bedrock rivers are found around the world in the mighty mountain ranges of the Himalayas, the Andes, the Rockies, the Sierra Nevadas, as we can see in these two photos here. Also, bedrock rivers are found in small streams in the interior of continents outside of these dramatic mountain ranges, like this lovely stream in the Flint Hills of Kansas. So in both cases, small and large bedrock streams set local base level for hill slopes and the rate of landscape response in response to changes in climate, changes in tectonic uplift, changes in base level fall. So most of the time, most bedrock rivers primarily incise vertically, carving deep canyons like in the photos we see at the top of the screen. So over the past few decades, the geomorphology community has made great strides in identifying and quantifying what controls the rate of vertical incision. So some of these important steps are listed here and some of the important foundational studies. But the main point here is that we know a lot about the controls on the rate of vertical incision and the processes of vertical bedrock incision. So many landscapes are not shaped by primarily vertically incising rivers, but by rivers that erode laterally or side to side, carving wide bedrock valleys. And when it comes to lateral bedrock erosion and the development of wide bedrock valleys, we know much less about these processes and controls compared to vertical incision. So a wide bedrock valley is a valley that has bedrock walls. Generally, the bedrock valley floor is covered in alluvium, but not always. And a wide bedrock valley should be several or many times wider than the channel that carved it. So in these two photos here, we have a wide bedrock valley in the Drôme River in France. This wide bedrock valley is 1 kilometer wide. The channel itself is 30 meters wide. And down here, we have a wide bedrock valley in the Buffalo River. Here, this valley is 500 meters wide. And again, the channel is 30 meters wide. So wide bedrock valleys are evidence of long periods of time when the rate of lateral erosion outpaced the rate of vertical incision, which is an unusual condition for most bedrock rivers. So when this lateral erosion rate exceeds vertical incision, that tends to be something of an unusual condition. So a relatively quick overview of what we know about wide bedrock valley formation. First of all, the importance of sediment. In order for wide bedrock valleys to form, lateral erosion rate must exceed the rate of vertical incision. And this can happen when sediment covers the bed, inhibiting vertical incision, but allowing lateral erosion on the valley wall to continue unhindered. So this role of sediment on the bed is so ingrained in our thinking that it's often considered a necessary condition for substantial lateral erosion and valley widening. So the next role that sediment can help play is, in order for wide bedrock valleys to form, the river has to erode the sides of the valley. And high sediment supply tends to encourage high channel mobility, allowing more frequent contact between the river and the valley walls and a faster rate of widening. So next, sort of primary control on wide bedrock valley formation is lithology. Of course, lithology is going to play a major role in the rate of bedrock valley widening and the ultimate width of the valley. So first of all, in softer rock, the lateral erosion rate, or the rate of undercutting on the valley wall, is faster. Softer rock is more susceptible to erosion. Also, in softer rock, in less resistant lithologies, we tend to find wider bedrock valleys compared to harder or more resistant lithologies. So we can see that nicely in these two maps of the Nehalem River in Oregon, with the terraces or the valleys colored in blue. So in this softer siltstone bedrock, we can see that these valleys are about 1 kilometer wide. And we can compare that to the valleys up here in the more resistant basalt bedrock, where these valleys are no more than 100 meters wide. Okay, so we know some key things about wide bedrock valley development in general. But what's not widely recognized is that creating a wide bedrock valley occurs in 2 distinct steps. So this first step is undercutting of the valley wall via lateral erosion. So that's shown here in these 2 upper pictures. Undercutting of the bedrock valley wall in this stream in Oregon in a basalt bedrock, and undercutting in the Buffalo River of Arkansas in a limestone bedrock. So some really great recent work has started to quantify controls on lateral erosion rates, this first step of bedrock valley widening. So my work over the past couple of years has focused on thinking about this second stage of bedrock valley widening, the collapse and transport of the overlying bedrock material. So this transport of collapsed overlying wall material this overlying material has to be transported away from the valley wall in order for lateral erosion and valley widening to continue. So that brings me to two key questions to address in this talk. First is, how is valley width influenced by the persistence versus mobility of collapsed material in the valley bottom? And next, what controls how quickly that collapsed material is moved away from the valley bottom? So in a couple of papers from a few years ago, I presented two end members, two sort of end member conceptual models or two end member mechanisms of valley widening. We call it first the resistant valley widening end member. So this would apply to a resistant bedrock lithology like granite or a massive limestone. So in this first figure, we have the river laterally eroding and undercutting this bedrock valley wall. After the valley wall is sufficiently undercut, the overlying material collapses into the valley bottom as large blocks that cover the valley wall and protect it from further widening. And here's an example of what this process may look like in real life with these large boulders covering the bedrock valley wall, and this is in Boulder Creek, Colorado. So in order for this valley to continue widening, these collapsed blocks must be eroded in size, eroded into a size that the river can transport before the valley wall is exposed again for continued valley widening. So this is our resistant end member. Our other end member is the erodible end member. So we start with the same figure of a valley wall being undercut by the river, undercut via lateral erosion. And in this case, the lithology is an erodible lithology, like shale or a weakly cemented sandstone. So after the wall is sufficiently undercut, the overlying bedrock collapses into the valley as small pieces that can be rapidly transported away by the river. And in this case, the volume of overlying material doesn't matter, because in this case, in this end member scenario, all of this material is easily transported away by the river. And here's an example of what this process may look like in real life. So in this mechanism, the collapsed material is transported away from the wall quickly, and the valley wall is rapidly exposed to further valley widening. So we wanted to see if evidence of these end member mechanisms and different rates of downstream valley widening exists in natural landscapes. So the results that I'm going to present in the next couple of slides are in my 2019 GRL paper. So in order to answer this question, I selected 5 rivers and tributaries in the Western Alps of France. And none of these catchments were glaciated during during LGM. So along the river distance, there are rapid variations in lithology along the river course in these folded and faulted Mesozoic sedimentary units. And the lithology here ranges from very resistant massive limestones, shown in pink in this map, to friable shales and marls, shown in blue. So zooming in on this figure, we can see wide bedrock valleys in the soft rock in blue, And we can see these abrupt narrowing in the valleys as we move through the resistant massive limestones. So at each one of these points, we extracted valley width, drainage area, and valley wall height from a total of about 1,400 different points. So to explain what we did with this valley width and drainage area data, I briefly want to explain this equation. So this equation here is a widely used power law relationship that relates valley width, WV, to a bedrock erodibility, K, and drainage area, A, raised to this exponent C. And this exponent C describes the rate of downstream valley widening. So this relationship has been applied in many previous studies across various different lithologies, and very often these previous studies have come up with a C value equal to about 0.4. So now we look at our valley width and drainage area data from the French Alps. And when we fit this power law to our data grouped by lithology, we find that the soft lithology group, shown here in blue, the C value, or the rate of downstream valley widening we get here, is equal to 0.42. For the intermediate lithology group, we get a C value of 0.27. And for the hard lithology group, shown in red, here we have the narrowest valleys, and we have a C value of 0.09. So really hardly any widening going downstream in these hard lithologies. So in our three lithology groups, we found three distinct C values. And these findings are consistent with model predictions, which I haven't presented here, but you can see more in Langston and Temme 2019. But these findings are consistent with model predictions, which suggest that the difference in C values is due to end member mechanisms. But we wanted to link lithology and mechanism more definitively. So we did that by looking at the relationship between valley width and valley wall height. So if a location or a lithology is following the idealized erodible end member, there should be no relationship between valley width and valley wall height. And this is exactly what we found in the soft lithology. Wide valleys exist in soft lithologies if valley wall height or relief is 5 meters, or if valley wall relief is up to 40 meters. But if a lithology is following the resistant end member, then valley wall height should limit valley width because the entire volume of the overlying material must be eroded and transported before valley widening can continue. And this is what we found in the intermediate lithology group. So in this figure, we can see that where valley wall height is low, wide valleys can develop in this intermediate lithology. But where valley wall height is high, almost no wide valleys develop, suggesting that the growth of the valley width is limited by valley wall height. And if we fit a power law to this data, this suggests a significant relationship between valley width and valley wall relief. So this relationship between valley width and valley wall height suggests that high valley walls limit valley width for the intermediate lithology group, but not for the soft rocks, which again is consistent with the valley widening end members. So in this study, this 2019 study, we show evidence for two end member valley widening mechanisms. And in this paper, we presented idealized end member mechanisms. But in nature, these idealized end members actually exist on a continuum. So this study was a springboard for me for thinking about different mechanisms of valley widening. So we know that lithology is important, and not just because of the erodibility, which sets the rate of undercutting, but lithology is important because it also says something about that collapsed material that falls into the valley bottom. So some other things that we wanted to consider are fracture spacing. So if we have the same lithology shown here in the Buffalo River, but different fracture spacing, the blocks that are released from this overlying overhanging bedrock material will be different sized blocks based on that fracture spacing and potentially have different widening mechanisms, even though we have the same lithology. The second thing to think about or consider is stream competence. So in addition to the block size that is released, these mechanisms depend on the ability of the river to transport blocks away from the valley wall. So if we look at this picture here, which is again a picture of Kings Creek in Kansas, this is a very small bedrock stream. And here we have collapsed blocks, collapsed limestone blocks protecting a shale bank. These blocks are about 40 or 50 centimeters in diameter. And here they're protecting the shale bank and acting in a manner of the resistant end member mechanism. However, if these same size blocks fell off the bank in our French Alps study area, this would very likely be much more easily transported. So this small stream in Kansas, Kings Creek, is the next piece of the story that I want to tell you here. So in this study, along with my former grad student, Abby Marcotte, who's now also at the University of Wageningen in the Netherlands. So with Abby Marcotte, we investigated bedrock valley widening on a bedrock stream in Kansas. So our field site is up here in Northeast Kansas, right smack in the middle of the United States. Our bedrock stream, Kings Creek, is located in the Konza Prairie LTER, which is a long-term ecological research station. And the general environment here is a native tall grass prairie. It's a really beautiful area, only 20 minutes away from the K-State campus. So the main points of this Kings Creek study that I want to share with you today are the in situ measurements of lateral bedrock erosion in 2 different lithologies, and also some observations of valley widening mechanisms in action. So here we are looking at a sort of overview map of the Kings Creek watershed. Kings Creek watershed is pretty small. It's 17 square kilometers. And from the ridge top down to the outlets, we have a distance of about 5 kilometers. So the lithology in this watershed is made up of thin interbedded units of resistant limestone and erodible shale. We can see that here in these 2 pictures of our 2 field sites in Kings Creek. So resistant limestone, erodible shale, these bands of resistant limestone sticking out, and erodible shale down below. So we had 2 field sites. The upstream field site is the North Fork field site located on this tributary of the main stem. And then only about 1 kilometer downstream, we have our second site, the nature trail site. But the nature trail site down here is downstream of the confluence of the 2 tributaries. So at our nature trail site, we had something on the order of about double the discharge compared to the North Fork location. Okay, so what did we do? We installed two transects of erosion pins at each site. So our 2 sites, Nature Trail and North Fork, and at each site, 2 vertical transects of erosion pins in both the banks and the bed. So we installed erosion pins into both the limestone bedrock and the shale bedrock. So I just happen to have some of these pins sitting close by me. If you guys are looking at the camera, this is one of our pins that we installed in the limestone. This is about 8 centimeters long. This is one of the pins, or it's actually a screw that we installed into the shale bedrock. So screw it in, sticking out, there we go. So in total, we installed about 27 shale pins and 20 limestone pins. So over the course of this 2-year study period, we measured the erosion pins 6 times. And Abby heroically measured these pins even in very cold water and even sometimes underwater using goggles if necessary. So that's real dedication to field work there. So also, in addition to measuring our erosion pins, we also monitored the banks with time-lapse cameras, which turned out to be really handy. Okay, so a quick transition into the results of this study. So the first result, part 1, is that our lateral erosion rates were super fast, like surprisingly fast, even in the shale. So we would expect the shale to erode pretty quickly. And our median shale lateral erosion rate was 94 millimeters per year. So just almost mind-blowingly fast. We're looking at this picture here. We're looking at a shale erosion pin where about 80 millimeters of shale bedrock was eroded in one single flood event that was occurred just before this picture was taken. So our second surprising result is that even the limestone experienced surprisingly rapid lateral erosion. Our representative limestone lateral erosion rate was 27 millimeters per year, which really is just surprising to me. When I installed these erosion pins, I thought maybe in 5 years, 7 years, I'll have measured a little bit of erosion. But no, this limestone in this area is eroding very, very rapidly. So looking at this set of pictures at the bottom, we are looking at the same group of limestone boulders over 1 year during our study period. And what we can see here is this group of limestone boulders, which, by the way, are situated more on the bank rather than on bed. So we consider these examples of lateral erosion. So what we can see here is that these limestone boulders are being, chunks are being plucked off, and in general, these boulders are sort of disintegrating through this extremely rapid lateral erosion. Okay, so for our results, part 2, the second lesson that we learned is related to the fate of collapsed bedrock wall material and the influence of its grain size. So here we are looking at a photo from a time-lapse camera directed at the North Fork transect. So this is the upstream transect. And the red dots down below the limestone boulder represent shale erosion pins, and these green dots represent a couple of limestone erosion pins. So note the time here. We are at 11:25 a.m. In the next photo, we are at 11:40 a.m. and we can see that this 1.5 meter diameter block has collapsed from the bank and completely covered all of our erosion pins in this area. So let me take us back one step. At 11:25, our limestone boulder is safely held in the bank. 15 minutes later, collapse and completely covering these pins. So this next photo that we're looking at is another time-lapse photo of the same location during one of the peak flood events in the summer of 2019. So here's that large boulder that collapsed from the bank. And this large block is still in the same position today, at least as recently as September of this year. So this series of very large discharge events in the summer of 2019 didn't move this block, didn't transport it away from the bank. Rather, the stream bed incised vertically around it. Okay, so now we are looking at the nature trail site, so downstream of the North Fork site. And at this site, the nature trail site, discharge is about double that of North Fork, the previous slides we're looking at. So at this site, limestone blocks also collapse from the bank onto the bed, shielding the bank from undercutting to some extent. But here at the North Fork site, the collapse blocks are quite a bit smaller, on the order of 20 centimeters in diameter. So looking at this next photo, which is from October of 2020, we can see that the bed and the banks are completely swept clean of any collapsed blocks that may have fallen off of the bank here. So the bed currently is also swept clean of this particular boulder, which is 90 centimeters in diameter. This boulder is now gone, transported downstream somewhere. And I know that because I was looking for this boulder because I recently installed several new limestone erosion pins, but the entire block was just moved before I had a chance to measure any of these. So here we're looking at time-lapse photos, again, from the nature trail site, the same site as the previous slide. On the left-hand side, we have the stream bank and bed before the largest flood event of 2019. On the right-hand side, we're looking at the stream bed and bank 24 hours after the flood event, which is a pretty massive flood event for this catchment. 3,000 CFS was the peak discharge here, or 85 cubic meters per second. So what do we see before and after this very large discharge event? We see a couple places are eroded from the banks, and we also see the emplacement of these imbricated boulders by this flood event. These boulders measure between 50 and 70 centimeters in diameter. And the point here is that here at this stream is easily capable of transporting collapsed material at this location, allowing lateral erosion to continue unimpeded by any large blocks that may collapse down and block that bedrock bank. So to summarize this study, first of all, there are very few studies that directly measure bedrock erosion in natural studies, especially lateral bedrock erosion. So that's a really cool outcome from this study. Second, our lateral erosion rates were very rapid, much faster than we had anticipated. And finally, our observations support that valley widening is more than just lateral erosion. It's more than just undercutting. Valley widening is also about the grain size of collapsed material and the capacity of the river to transport that material away from the valley bottom so that lateral erosion can continue. So this local study on Kings Creek helped inspire my thinking about the nature of collapsed material and how that influences valley widening. And inspired my new project, brand new project that I have going on the Buffalo River in Arkansas. So this is a new project that I just started with my co-PI, Jill Marshall. And my grad students, Olivia and Clay, are working on this project as well. And the goal of this project is to explicitly evaluate the role of valley cover on bedrock valley width. And I'd also like to give a quick shout out to Amanda Keene-Ziebert for introducing me to the Buffalo River as a field area, sort of with our geomorphic science goggles on. So the Buffalo River is located here in Northwest Arkansas. So the Buffalo River is a national river. It's under the jurisdiction of the National Park Service. Buffalo River is undammed along its 200-kilometer course, and it's one of the last undammed rivers in the lower 48 United States. The Buffalo River cuts through the Ozarks Plateau, which consists of horizontally bedded sedimentary units. These horizontally bedded units are shown nicely in this picture of Hemden Hollow. Hemden Hollow is the tallest waterfall between the Appalachians and the Rockies. Hemden Hollow is over 200 feet high, or around 60, 65 meters high. And you can see the people down here for scale. This is a very substantial, very tall waterfall. Okay, here I just show an overview map of the Buffalo River watershed with the sampling locations in black that we have visited so far. We have 32 locations that we visited so far. And I've also colored this map by the two important lithology units that we will discuss later. So in the next slide, we are going to zoom in for a closer look into this section of this upstream area of our study area. Okay, so now we're looking at a slope map of this upstream section of our study area. So flow direction is to the north, to the top of this image. And we can see the valley bottom nicely colored in blue. So this low slope valley bottom. And the white dashed line that I have drawn in here is the lithological transition. So we can see the effect of this lithological transition on valley width. So if we look going downstream, we have wide valleys up here in the upstream areas. As we go downstream, valley width gradually narrows going downstream beyond this lithological transition. So in the downstream sections, we have the Everton Formation, and the upstream sections, we have the Boone Formation. So first, just show you a couple of cross sections of the valley in the Boone Formation in these wider valleys. So in the Boone Formation, the valley width ranges from about 300 to 1,000 meters wide, and these valleys widen going downstream, as we might expect that a typical valley would. Typical valley would widen going downstream, just as a typical channel would widen. Bedrock channel, alluvial channel should widen going downstream. Next, look at a cross section from this downstream area in these narrow valley sections. In these sections, these downstream sections in the Everton Formation, valleys are narrow, less than 200 meters wide. And in this downstream section, the valleys really don't widen at all. They're pretty consistently around 200 meters or less. Excuse me. Okay, so clearly, in this location, valley width is controlled by lithology. So I want to talk just a little bit more in depth about these two different lithologies. So the wide valley lithology, the upstream lithology, is the Boone Formation. The Boone Formation is a thinly bedded cherty limestone, but the Boone limestone still has some decent cliffs, some pretty decently vertical, tall cliffs. These aren't crumbly. And we have wide valleys in the Boone Formation. The Everton Formation is our downstream lithology and is variable in terms of its composition. It's made up of limestones, dolostones, sandstones. It's also variable in terms of the density of its discontinuities, so the fracture density and bedding plane density. So what's really interesting about these two lithological units is that these two units have the same surface hardness from Schmidt-Hammer measurements. Same surface hardness. Two studies have shown this. And as a matter of fact, the Boone Formation has slightly higher surface hardness from Schmidt-Hammer measurements. So what does this hardness value mean? Surface hardness is a proxy for erodibility. It allows us to characterize rock strength or erosional resistance. So if it's not rock strength that controls valley width here, that suggests that other bedrock properties like solubility or fracture density or characteristics of talus piles play a role in determining bedrock valley width. So coming back to some of our key questions from earlier, in order to start answering these key questions, I want to start with just some initial research questions that we've just started answering in the Buffalo River. So what are the characteristics of the talus piles in the wide valley and the narrow valleys? And we're going to be measuring and calculating some of the factors that control the removal of the talus piles, like grain size, like shear stress for the river, and the volume of the talus piles. Okay, so here we are zoomed into another view of our upstream valleys, our wide valleys. Here the valley is between 600 and 800 meters wide. This is a geological map of the area, and on this map we have a bunch of different locations plotted, and these are our potential sample locations. We didn't sample at every single one of these. So I want to show you a couple of pictures of what does the talus look like in these wide valleys. So in the wide valleys, our talus piles tend to be more discontinuous or even cone shaped. So here we have these individual cones of talus. And in this bottom picture, we have the main talus pile here. It sort of peters out into bare bedrock as we go downstream. And the other thing to note in these pictures is that these wide valleys in the Boone Formation still have tall and cliff-forming bedrock valley walls. They're not just a crumbly mess. Okay, so looking at a similar figure, but now we're in the narrow valleys, where valley width is 200 meters or so. Again, geological map, we didn't sample at every single one of these sites. And I want to show you some pictures now of talus piles in the narrow valleys. So here are two talus piles in the narrow valleys, two different locations. But what we can see here is that talus tends to be more abundant in the narrow valleys. Many of our talus piles are continuous kind of blobs of talus that sit below these bedrock walls. So these pictures were taken on our first sampling mission in the winter, which is great for being able to see and measure the talus. And this is a picture of a talus pile in the narrow valley during the summertime. So the vegetation during the summer was a major problem in terms of access to the talus and visibility. So a couple of fieldwork pictures. We kayaked down the river to reach our sites most of the time, which was just amazing. You know, one of the best parts of having a job where you can do research. And at each location, we measured the grain size of the talus, measured bedload grain size, wall height, talus pile volume, bankable width, etc. And here are Clay and Olivia measuring talus piles here. Okay, so let's have a look at some of our preliminary data. So at each location, we measured bedload grain size to characterize the sediment sizes that are transported by the river during, say, a 2-year flood. So in this figure and in the couple figures following, I'll have the D50 grain size plotted in the solid marker in the middle, and D84 grain size in the bar at the top, D16 as the lower bar. And on the x-axis, we have our sample locations ordered from upstream to downstream. In real life, these are not equally spaced. For this figure, they are. So what do we see in bedload grain size? In general, bedload grain size decreases going downstream. That's not a surprise. Our slope also decreases going downstream. And this is over a river distance of 48 kilometers. So here we are looking at talus grain size, not bedload grain size. Again, our D50 talus grain size is shown by the center marker, and D84 by the upper bar, D16 by the lower bar. Okay, so what do we see here? First thing that I want to point out is that in the Everton formation, in these narrow valleys, talus grain size is remarkably consistent across these 37 kilometers of river distance. So not a great deal of variation in talus grain size going downstream. The second thing that we notice is that talus grain size is much more variable in the Boone formation, which is over a river distance of only 11 kilometers. So in the Boone formation, talus grain size ranges from comparable to the Everton all the way down to very small D50 talus sizes of less than 100 millimeters. And just to point out, this pink location is a talus location, or a site location where we only had 6 talus grains total. So we measured them. However, we don't find that to be a representative sample, so we will discount that location for the rest of this. Okay, so here's another way to look at this talus grain size data and compare the talus sizes in the Everton versus the Boone. So here we have a cumulative frequency figure with grain size on the x-axis and the blue arrow pointing to where we would locate our D50 grain sizes. So again, we see that talus grain sizes in the Everton, the narrow valleys, are remarkably consistent in size. Now we add the cumulative frequency curves for the Boone formation, the Boone locations in green on top of the Everton. And we can really see the striking difference between the two populations of talus in terms of the spread in their D50 grain size and our D84 grain size for that matter. So the largest grain sizes in the Boone talus are comparable to the Everton, but get much, much smaller talus grain sizes in the Boone compared to the Everton. Okay, so next on to the real meat of this. Comparing bedload grain size, or the grain sizes the river can typically transport at that location, with talus grain sizes, this collapsed material that's blocking the valley wall. So what we can see here is that there is no overlap of talus and bedload grain size in the Everton. So in no location does the D84 of the bedload overlap with the D16 of the talus. However, in half of our Boone formations, there is overlap between the talus and the bedload grain size. So this tells us that at the overlap locations, the river can potentially move some talus grain sizes as bedload, at least occasionally during that 2-year flood. And this also tells us that in a typical flood that moves bedload, the talus in the Everton has no chance of moving at all. So we wanted to look at this potential transport a little bit more closely. So we did this by calculating a bed shear stress using field measurements like bankable width and slope, and by using a discharge for the 2-year flood at each location that we calculated from 4 discharge gauges on the Buffalo River. We also calculated critical shear stress for the bed shear stress necessary to potentially start moving certain grain sizes, in this case, the D50 and D84. Okay, and yeah, let me explain this one quickly, but it's not the most interesting one. I do want to get to the last 2 here. So what we have here is we have the shear stress, bed shear stress for the 2-year flood, the ratio of bed shear stress for the 2-year flood over tau crit on the y-axis, and our sample locations going downstream. So where tau over tau crit equals 1, this blue line, this is the threshold of motion. This is where bedload transport can potentially start happening. So in this figure, where tau over tau crit is greater than 1, that means that transport is possible and even likely. Okay, so let's look at the couple more interesting figures. So here we're looking at bedload, potential bedload movement. And not surprisingly, the bedload can move under the 2-year flood. So now we're looking at the potential transport of talus by that same 2-year flood as before. And the figure again shows a ratio of the bed shear stress for the 2-year flood over the tau crit for the talus grain sizes. And again, where tau over tau crit exceeds 1, then transport of this size is possible. So what do we see here? The 2-year flood is not really that close to transporting any of these grain sizes in the Boone lithology, except 2 locations here and here. And talus is even further from this threshold of transport in the Everton location. So this talus gets harder to transport going downstream because 2 reasons. The talus size does not decrease going downstream, but the bed shear stress does decrease going downstream. So we can see a difference in these ratios between the Boone and the Everton. So we're not getting movement of talus in this 2-year flood. So we wanted to look at potential transport of talus by a 1,000-year flood. So we calculated the value or magnitude of this 1,000-year flood at each of our sample locations from flow frequency curves from the 4 discharge gauges on the Buffalo. And this figure is the same as before. And what can we see here? You can see that the 1,000-year flood transports nearly all talus grain sizes in the main stem of the Boone Formation. Nearly all, but not every single one. We also see that the 1,000-year flood transports the D50 grain size at less than half of our sample locations in the Everton Formation, and the D84 grain size of the talus is only transported at 1 location here. So main point number 1 from this figure is it looks like the Everton talus is potentially transported less frequently than the Boone talus. Again, due to both grain size, so this Everton talus is larger than the Boone talus in general, and the transport capacity of the river. Our shear stress decreases going downstream in the Everton. Our main point number 2 is we're thinking about the persistence versus mobility of talus grains. The magnitude frequency distribution of flood events in a particular location is really important. So if the 100-year flood is only twice as large as the 2-year flood, there's far less potential talus transport than if that 100-year flood is 10 times as large as the 2-year flood. So some summary of our early buffalo results. We found that we have different characteristics of talus in the wide and the narrow valleys. And for more details and discussion on this, I encourage you to see Olivia Grover's AGU poster this year in 2021. So the second main point of these early buffalo results is that we found that talus can be potentially moved more frequently in the Boone Formation. So related to this, we need to be thinking about what's the volume of the talus in the Boone and Everton valleys, and can we calculate timescales of talus evacuation in the Everton valleys versus the Boone valleys? And for more information on this, please see Clay Robertson's AGU poster this year. Okay, so just some final thoughts, kind of wrapping up thoughts. First thought is that bedrock rivers are all around us, and we can learn things from exploring in our own backyard, so to speak. So these opportunities to learn about the world around us are everywhere. So this idea is kind of coming from, I was just really pleasantly surprised to find that there are bedrock rivers here in Kansas, and that we got a really nice paper with some really interesting results from this bedrock river in Kansas that ultimately helped guide my thinking forward into this Buffalo River project. So lithology matters for the rate of widening and final valley width. Lithology influences the rate of lateral bedrock erosion, which we already knew. But in order to widen the valley, we also have to remove the collapsed material from the valley bottom. And lithology is a key control on the characteristics of collapsed talus in terms of its grain size and how quickly these blocks can weather and disintegrate into transportable sizes. And valley width is controlled by the mobility versus persistence of collapsed wall material. And this persistence versus mobility of collapsed talus is controlled by both the grain size of the talus and also the river transport capacity, particularly the magnitude of these largest flood events. And so with that, I just want to say thank you to everybody for joining, and I want to give a special thank you to old friends and even old professors from the University of Florida and University of Colorado that I'm told are out there in the audience. And so thank you. I will now take some questions.
Wonderful. Thank you so much, Abby. That was really great. So you all know the deal. If this isn't your first Landscapes Live rodeo, we've got questions coming in the chat. Myself and Michal will take turns reading those out. Feel free also to raise your hand and we'll kind of try to work you in the order we get your question. So I will kick it off here. We've got Matt Covington asking, have you thought about contrast in talus erosion processes? The Boone Formation can rapidly dissolve, order 1/10 of a millimeter a year, whereas the Everton cannot.
Yeah, definitely. We have thought about, so we have the size of the block size that the talus arrives at the valley bottom. They arrive in a certain size, but then part of that, the next part is how do they decrease in size to a size that the river can transport? And definitely the solubility is potentially a key factor here as well in the Boone limestone. And the Everton, Matt is familiar with this area. And in the Everton, we have sandstones, and in many places, the sandstones are dominant and create these very tall cliff forming units. But the Erosion also has limestones and dolostones, which also may not be as soluble as the flume limestone, but yeah, that's definitely something that we are thinking about and considering.
All right, then I'll move on to the next question, which is by Kirsten Chilton. Within the Everton, did you notice if any of the sub-lithologies dominate the talus? I'm wondering if that one massive sand unit is producing most of the immobile talus and therefore directs the narrow width response.
Yeah, so that's a good question. And that's kind of one of the conclusions that Amanda Keen-Zieber and her team came to in their 2017 paper, that this massive sandstone unit, the Newton sandstone, is really dominating the talus piles and the valley narrowing. However, as you move further downstream, that massive sandstone unit pinches out, yet we still have abundant talus, very large talus, even when we have no sandstone unit in the walls above. So that's definitely, I would say that's a definite possibility as to playing a role in keeping the valleys narrow, but I think that's not the entire story here.
Okay, so we've got another question from Haley Springston asking, how did you measure talus grain size for talus blocks that are partially submerged in alluvium?
Well, for that, we pretty much just did our best. If we could pull the talus block out of the alluvium a bit, you know, we could pull it, clear it, measure it, and if not, yeah, we did our best to measure that B axis, the intermediate axis of the talus grains.
All right, last call here, folks. Any other questions in the chat or anyone want to raise a hand and chime in? Okay, we will close it up there then. Thank you so much again, Abby. That was a really stimulating talk. Before everyone goes, I would just like to advertise, we do continue next week with Sarah Savi, the week after with Kate Huntington. We then take a brief break for Thanksgiving and follow that with Dirk Scherler, Anna Bernhardt, and Sebastian Carretier. So it's an all-star lineup running all the way through basically AGU. So please keep coming back for that. So thanks again, Abby. We really appreciate it.
Yes.